Okay, so let's go over deletion. Or, yeah, binary search tree deletion. So, okay, so the way this works is fairly similar to insertion. Recursion is also used. So let's say you wanted to, delete the item E from the tree. So you would specify the item, of course, and then you would ask, well, is this item smaller than the root? No, it's not. Is it bigger than the root? Yes, it is. So we go here. So this is the first recursive call. Then we just simply say, well, delete it from the right subtree. This part. Then we ask the same question again. Is the item smaller than the root? In this case, yes, it is. Okay, so then we delete the item from the subtree, this part. Okay, and then we ask that again. We say, is the item smaller than the root? No. Is the item bigger than the root? No. Well, is the item equal to the root? Yes, it is. Okay, so now we know that this is the item we're actually looking for, so we can go ahead and just delete it. So that's pretty straightforward, because E was a leaf. Now, let's say we wanted to delete C, which is a little bit more involved, because C is not a leaf. You can't just delete a node that has leaves, because if you did, you would not only delete that node, you would delete all of its leaves, since you're cutting off the reference right here. Okay, so you would locate your node, the one you were looking for, and saying, okay, so this is the node that we wanted to delete. And then there's several cases, and I'll just quickly outline them here. No, sorry. Okay, so case one. Case one is that the node that you're deleting has no children. Which means that it is a leaf, which means you can just delete that node. Case two is that the node has a right child. Like so. So if it's C, that means C simply had one child. And I guess there's a better way to say that. Case 2 should be node has no left child. So there's just one child. In this case, you can simply move the child up, effectively deleting C. Okay, so you would delete the reference to C and move the child up. Case 3 is pretty similar, and it just states node has only a left child. And that would be if C simply just had A as a child, in which case we do exactly the same thing, except the other way around. We delete C and we move A up. And case 4 is if node has both a left and a right child. And this is by far the most complicated step, because you have to make sure that when you're deleting, you still, after you delete, the binary search tree that you then return still has properties of a binary search tree, meaning that every node on the right has to be bigger than the root node, and every node on the left has to be smaller than the root node. So let's give an example for this. So this is your the little subtree we would have to deal with if we wanted to delete C. Now, in order to maintain the properties of a BST and delete C, you would have to move B up and B's left child would have to be A. Okay, so again, you would have to move B up and B's left child would have to be A because A is less than B. Okay, so moving B up and deleting C. Okay, now at least I think that's well, I mean, in a case, so let's look at how this would work if the tree that we were dealing with was a little bit more complicated than just being a root and two children tree. So let's say the tree actually looked like this. Or actually, we'll take the original tree. C, A, B, F, E, and G. So let's say we wanted to delete D. Well, in this case, what would we have to move up in order to maintain the properties of a binary search tree? We couldn't move F up because E is less than F. So if we moved F up, we would have to move E to the left-hand side of F and effectively restructure the tree something similar to this. And that's not very efficient since we want to ensure that the tree is kind of balanced and that the heights are as equal as possible. A much more effective way to delete D would be to make E the new root, therefore rebalancing the tree like this. And that's much more balanced. Okay, so that means that we have to find the item that's closest to D but the smallest on the right subtree, which will always be the leftmost node of the right subtree. Okay, so now let's try to write some code for that then. So as always, when you're deleting, of course, you want to specify what tree node this item is supposedly in, and of course the item that you want to delete. Now, if the node is null, that means that the item doesn't exist because the entire tree was traversed by the rules of binary search trees and the item was not found. So in which case you can either return null or throw an exception if you want to. Maybe print a message that the item doesn't exist. Otherwise, the item has to be somewhere. So if the node, and this is, pseudocodish, if the node is bigger than the item, or rather, let's say if the item is smaller than the node, then the item has to be on the left-hand side. So we will simply say, well, this node's left child is going to be its original tree, its original left child, without the item. So we're going to delete the item from the left child and then substitute that in for the original left child. Okay, otherwise, the item may be bigger than a node, in which case we would do exactly the same thing, except for the right child. Okay, so that's if the node is smaller than if the node is equal to. But there's a third possibility, which is if the item is the node. Okay, and this is the more complicated step, which usually is done in another method. You would simply have a helper method where you would simply say, for example, delete like this. Okay, so you could make a helper method that deletes a node instead of an item, and in that helper method you could then make sure that you accommodate all of the different cases. So, but right now we're just gonna put the code inside of the delete method and not bother making a helper method. So, okay, let's go through our cases then. Case 1, the node has no children. Okay, well, if node dot left child, oh, I'm sorry, is null, and node right child is null. Well, then that is the easiest case, in which case you can just simply set the node to null, or return null. Because remember, up here we're going to set the parent's left or right child to null. So if node left child and node right child is a leaf, then its parent simply gets a null, meaning that leaf is now gone. Otherwise, node left child may be null. In which case you would have to simply return the node right child. So, another example, you have your parent, you have your node, you have the right child of the node, and of course nothing in the left child. We wanted to delete the node. You'd simply return the right child of the node, and which becomes the new child of the parent, effectively making the tree look like this. Bam. And it's deleted. Okay? Case number 3. The node has no right child. In which case we return the left child. And I mean, you kind of get the picture of what this would look like. It would simply, pass L to N, and effectively therefore deleting N. Now our last and very final case is that node has both a left child and a right child, and usually that's a problem because it's a little bit more complicated. You have to find a proper item to replace node with. Now, just a note, returning node right child means that if right child is a subtree and has a whole bunch of other stuff attached to it, that hierarchy gets conserved because we're passing right child onto the parent, meaning whatever is attached to right child is then attached to the parent as well. Okay, so using this works quite nicely. Now, if the node has a right child and a left child, then we need to find, as mentioned earlier, the leftmost node of the right child, which would then be the new, replace the node and deleting the node effectively. So, what we want to do is, and I'm gonna not bother writing out the code that looks for the left child and looks for the leftmost and deletes the leftmost, because that's simply a tree traversal, and I mean, if you should be able to do that yourself. So let's say we will return, or actually, we will store the new node, or the node, we'll just call it n, leftmost of our current node, it's the right child, which will be a leaf. We'll simply store that. Then we will delete the leftmost item from the current right child. And there's a little bit cleaner way to do this, so we'll see that in a second. And then we will set the node's item equal to the item of the leftmost, therefore deleting the item of the current node and achieving our goal. So we'll set node dot item equal to n dot item, which I guess we could have done up here. And then we will return the node, the updated node. And that's really all that there is to deleting. Okay, so let's look through it again. So there's 4 cases. The node has no children, the node has a right child, and the node has only a left child, or the node has both children. Now if the node has no children, then it's a leaf, and it's pretty easy, we just set it to no. Otherwise it's more involved and involves passing on the left or the right tree, subtree, or child onto the parent. So here's the code, or the pseudocode. Let's look at actual code from the assignment. Oh, sorry. Okay, here we go. Delete item. Okay, so if the node is null, then the item wasn't found. Otherwise, we will have to search for the item some more. So, if the search key is equal to the current item, then we found the node that we want to delete, in which case we simply delete the node and then pass it onto the current tree. Otherwise, we do the recursive part. If it's smaller than, then we search the left tree. If it's bigger than, we search the right tree. Now, the code for deleting a node. So here, case 1, the node is a leaf, meaning the left child and the right child is equal to null, in which case we simply return null, effectively deleting the leaf. Case 2, the node has no left child, aka only has a right child. So this is the if statement, in which case we would simply pass on the reference of the right child to the parents, deleting the node and maintaining the hierarchy of the tree. Case 3. The node has no right child. Then we simply pass on the left child, or left subtree, and maintaining the hierarchy of the BST. Otherwise, the node has both children. So here we simply get the replacement item. We find the leftmost item of the right subtree. Then we replace the item in the node with the replacement item. And then we delete the leftmost item from the right subtree and return the node. The edited node, meaning the item has been updated in this and the leftmost has been deleted, okay? So again, you find a replacement item, you update the node, deleting the current item, the item that we wanted to delete, then you delete the leftmost in order to not have duplicates, and then you return the updated node, okay? And this node is then going to be stored in the tree. So because of recursion, this is going to pop up all the way to the root node, the original root node, with just that one item deleted. Okay.